In this new section, we are also going to solve using undetermined coefficients, but the approach we're going to use is going to be a little different, or possibly a lot different. We're going to use the annihilator approach. Now, first we need to talk about linear operators. Linear operators are just like functions. Like earlier in algebra, if you had to find f plus g plus h of anything, 3x minus 2, you would have f of 3x minus 2 plus g of 3x minus 2 plus h of 3x minus 2. And if it was being composed, first you would take h of 3x minus 2, and then whatever you got, and what's in that bracket, you would then take g of that. And then whatever you have after doing g, you would take f of it. Now, linear operators are pretty much the same. Suppose we have this polynomial, x cubed plus 4x squared plus 5x plus 2. We want to operate on that polynomial with this linear operator. It's customary to put linear operators in brackets. And we're going to put d squared plus 5d plus 6. Now these are functions. D squared means take the second derivative of this polynomial. 5d means take the derivative of this polynomial, multiply it by 5. The 6 is just the function, multiply it by 6. So just so we have these derivatives in front of us, that's the original function. And if I were to take the derivative of this function, I would get 3x squared plus 8x plus 5, the derivative. And if I have the same original function, but I want to compute the second derivative, well then I just take the derivative of this, which is 6x plus 8. Okay, but first I want the second derivative, which I already have. It's 6x plus 8 plus 5 times that derivative. There's the 5 times, and now I'll put the derivative. 3x squared plus 8x plus 5. Right there. Plus 6 times that polynomial, which will be 6x cubed plus 24x squared plus 30x plus 12. In this step, I'll just distribute the 5. You have 6x plus 8 plus 15x squared plus 40x's plus 25 plus the rest. 6x cubed, etc. And I'll combine like terms. Remember, terms are just separated by addition and subtraction signs. Coincidentally, there's no subtraction sign, but that's not a big deal. Those are the terms. We want to combine like ones. Only one term has an x cubed, and that term has 6 of them. How many x squares do we have? You should not say that you have 2 of them, like 1, 2. Rather, you have 15 plus 24, that's 39. You have 39 x squares. And when it comes to x's, you have 40 plus 30 is 70. And looks like that's all we have. But for some reason, I think that's wrong. Okay, let's see what went wrong. Well, nothing went wrong. We have 40 and 30 is 70. Let's not forget that one over there. 76 x's. In fact, let's make believe that I didn't see that one. Let's make believe I didn't see it. Let's even circle it like before. And I will put down 70. Now the constants. We have 8 plus 12 is 20 plus 25 is 45. Now you should look here. You should look here and see, is there anything that wasn't crossed off? That's why I'm crossing things off. And I say, oh my, I didn't take care of the 6 x's. So I'll add those 6 x's. Some are already 70 x's. And I get 76 x's. So now this is the answer. 6x cubed plus 39x squared plus 76x plus 45. Now, we're going to do this problem all over again. We're going to do it slightly differently. So we still have d squared plus 5d plus 6, and that's going to operate on this polynomial. But what we can do is, if we thought of d squared plus 5d plus 6, and I'm not going to prove or argue why this is valid. If we thought of it as a polynomial, then you can factor it as d plus 3 times d plus 2. But it's not really times, it's composed. This is d plus 3 composed with d plus 2 operated on this polynomial. Now, I said earlier how composition f circle g of x is first you do g of x, that is, in our case, first you do this, and then you take f of that. Okay, so you don't even need this composition symbol anymore. Absolutely, I could have done d plus 2 composed with d plus 3 operated on this polynomial. I could have done that. So let's actually do this. So what's inside the red brackets, whatever it ends up being, I'm going to take d plus 3 of that. Well, first I take the derivative of what's in the brackets. I get 3x squared plus 8x plus 5. Then I add on 2 times what's in the brackets. 2x cubed plus 8x squared plus 10x plus 4. And before I do d plus 3 on what's in the bracket, I choose to combine my terms. I don't have to, but I will. I only have one term that has x cubed. X squared I have 2. That's 3 here and 8 there. That's 11x squared. And here I have 10 x's plus 8 x's. That's 18 x's. And then 5 plus 4 is 9. And I just look to see if I crossed off everything. I looked to see if I crossed off everything in there, and I did. So now we're ready to operate in that polynomial with d plus 3. That is, first I take the derivative of what's in this bracket, which is 6x squared plus 22x plus 18. And then I add on 3 times it. 3 times 2x cubed plus 3 times 11x squared plus 3 times 18x plus 3 times 7. And what I'm going to get is 6x cubed, 33x squared plus 6 more, 39x squared, and 54 plus 22 is 76x's. When I add those constants, I get 45. And I smile because I got the same answer that I did up there. So this is how you operate with linear operators. Linear operators work on polynomials or trigonometric functions. I could have done the same operation that I have to the left on 3 sine x minus 4x. I could take the second derivative of this and then add on 5 times the derivative of this and then add on 6 times this. And I'd get what I get. I hope that you learned how to deal with linear operators. Now, linear operators, like we just dealt with, d squared plus not 5x plus 5d plus 6, we generally call them L. We generally call them L. And they can even work on what you put here. It can be a differential equation, actually. Now, let f of x be sufficiently differentiable. Remember, some functions, you can't keep taking a derivative of them. But as long as we can take the derivative of f of x enough times that we need, as many times as we need, we're in business. Okay, we say that L, the linear operator, is the annihilator of f of x if you apply L to f of x and you get 0. It annihilates it. For example, d squared of 3x plus 4. Well, here's 3x plus 4. That's the first derivative, and that's the second derivative. It annihilated it. Of course, if we took the fourth derivative, we did d4, it would also annihilate it. Because here's the original function. That's the first derivative. That's the second derivative. And the derivative of that, which is again 0, is the third derivative. And the derivative of that, which is 0, is the fourth derivative. But one should always try to find the least power, the least number of derivatives that will annihilate it. So let's look at some annihilators for some set of functions. Suppose you have e to some number x. I claim that d minus a will annihilate e to the ax. And, I can be wrong. Let's prove it. I take the derivative of that, which is a e to the ax, and then I take away a times that. A times e to the ax. Ooh, I get 0. I get 0. Now, what if I have e to the ax, I put an x in front of it? Well, then I claim that you do d minus a 2 times. That is d minus a of d minus a on that function. Have to do d minus a twice. So here's their d minus a we're going to do the second time. And again, I should be using those closed brackets. Sorry about that. But first I take the derivative of that. The product. I take the derivative of the first term, which is 1, times that function, which is just that function, plus the first times the derivative of the second, which will be a times e to the ax. That's what I got when I did d of this. Now I'm going to take away a times that, and I'll get negative alpha x e to the alpha x. And of course, this will cancel out, so I just have to do d minus alpha on e to the alpha x. But I'm not going to redo it because I did it up here and I did get 0. Okay, so that's pretty cool that I get 0. Now, this pattern keeps working. Let me just erase some of this stuff. You may say, what pattern? In fact, let me write it so there's no writing at all on the board. D minus a, when it operates e on e to the ax, we get 0. When we want to operate on x e to the ax, we also do d minus a. We have to do it twice. And when you have x squared e to the ax, and you want to annihilate it, you want to get it to 0, do d minus alpha 3 times. So if you had d minus a to the nth power, what should the power of x be? What power goes here? Well, if you think about it, this was x to the 0, but that understood power out there was 1. Hard to write a 1. And when the power was understood to be 1, we put 1 more, we put 2. When the power was 2, we put 1 more. Or working the other way, if the power out here was 1, that power was 1 less. That power is 1 less. If this power here is 3, you can have x squared. If this power is n, we're gonna have 1 less. It's gonna be x to the n minus 1. And do our proof by by induction to show that this always works. This will always work. Okay, so again, if you want to annihilate e to the negative 5x, so one other thing which I failed to bring up. If the power is a, then we do d minus a. The power is a, we do d minus a. The power is negative 5, we do d minus negative 5. That is, we'll do d plus 5. You get 0. You have e to the, or x cubed, e to the negative or positive 7x. You want to get 0. You do d minus that number. Okay, and since this, and then you have to decide on the power, and the power out here. If that's a 3, you do it 4 times. You need to be able to walk down the street and recite that. So, now somebody asks you, what differential operator will annihilate this? It needs to just be first grade. You're going to say, well, it's going to be d minus that number raised to the 1 more in the power of x, which 1 more than 27 is 28. You need to be able to save that. So, if I were to ask now, again, if something annihilates something, if d minus alpha annihilates, well, let's do a real one. D minus 5, it annihilates e to the 5x. And for the record, it does. The derivative of that is 5e to the 5x. And then you take away 5 times that. And you go, oh yeah, that's 0. If this is already 0, then if you put another operator here, like take the second derivative and then add on 4 times. Well, what's in this bracket is 0. So d squared plus 4, when it operates on 0, it's still going to be 0. Because the second derivative of 0 is 0, plus 4 times 0 is 0, you're going to still get 0. Once you annihilate something, and this annihilated that, anything you do out here won't matter. If I took the third derivative and I took away 4 times the derivative and added 4, it wouldn't do anything. Because we just said that this mess was 0. I said it right here. This mess was 0. And now you're doing a linear operator on 0. What's in this big red box is 0. Okay. So for example, you have e to the 5x, and you know that d minus 5 will annihilate it. You can put the power 17 up there. Because that just, okay, let's just put 3 so I can write it nicely. So you're going to have d minus 5, d minus 5, d minus 5, operated on e to the 5x. Well, first you do that, but that's 0. And then you do d minus 5 on 0. Well, that mess is 0. Then you do d minus 5 on 0. When you do linear operators on 0, you keep getting 0. Okay. So, I'm going to do a little exercise. The instruction is to find the differential operator that annihilates these. What would annihilate this? What would annihilate that? What would annihilate this? What are the annihilators? Well, here, if you just took the 5th derivative of this, you'll be okay. Sorry, the 6th derivative. You take the 6th derivative, you'll be okay. Just for the record, if you have, say, x cubed, how many derivatives will you have to take? If the degree was 3. Well, this is the first derivative, and brings it down to a quadratic. The next derivative brings it down to linear. The third derivative brings it down to a constant, but it's the fourth derivative that brings it to 0. It's always going to be one more than the power. If you had x to the fifth, you're going to have to take 6 derivatives. The first derivative will be 5x to the fourth plus lower terms. The next derivative will be 20x cubed plus possibly lower terms. That could be at 4x to the fourth. 48x squared. And the next derivative will give you a quadratic. And the next derivative will give you a linear. And then the fifth derivative will give you a constant. And it'll be the sixth derivative that gives you the 0. Fine. The lower terms went out more quickly. It only took 5 derivatives to kill this off. That part was still there after the fourth derivative. The 3, it was killed after the first derivative. So we want to kill the whole thing. We want to kill off the highest power. Now, what about e to the negative 5x? What about e to the negative 5x? Let me write that a little bit higher. E to the negative 5x. Well, d minus that number, negative 5. So d minus negative 5 is d plus 5. That will annihilate it. And that problem is done. Now, what will annihilate this? Well, first let's copy it down, right? What will annihilate this? Now first, so let's just talk about annihilating this. What you need to remember is that something that annihilates the function will annihilate the constant times the function. So these are differentiable operators. When you take the second derivative of our constant, k times the function, just like when you take the derivative of 3 times x squared, the derivative is just 3 times the derivative of x squared. That is, the constant comes out in front. Even if you want to take the second derivative, that 3 comes out. Just take the derivative of the 2x now. This is k times the second derivative of f of x. Constants always come in front. It doesn't matter whether it was the second derivative or the nth derivative. Any derivative. It wouldn't matter. Okay. If you want to annihilate this term, if you want to annihilate e to the 3x or negative 2e to the 3x, you want it to be 0, well then you should do d minus that number. That will annihilate it. Now, if you want to annihilate this, since the power of x is 1, if you want to annihilate 5x e to the 3x, well then you should do d minus 3 minus 3 twice. But you know what? If we did it to the top one twice, this one, we put a twice up there, it wouldn't matter. Because once we do d minus 3 on this one time, we get 0. And when you do the next d minus 3 on the 0, you're still going to have 0. Okay. Now, remember that if you have d squared plus 4d minus 5, and you do it on a sum, f of x plus g of x. Well, when you do the second derivative on a sum, derivatives are linear. It's the second derivative of f of x plus the second derivative of g of x. And then you do 4 times. You get 4 times the derivative of f of x plus 4 times the derivative of g of x. And then you take away 5. Take away 5 times f of x. Take away 5 times g of x. Now, if you were to combine like terms, like all the f of x's, this term and this term and that term, well, that's nothing more than d squared minus 4d plus 4d, minus 5 operated on f of x. Plus, do the same with the g's. You got d squared plus 4d minus 5, all operating on g. Okay. So what I'm getting at after talking about this theory here is that to annihilate this here, let me write it down neatly, to annihilate this here, all you have to do is do d minus 3 twice. And the one above, you only needed to do it once. For once wouldn't annihilate this. 2 times using d minus 3. So the answer is d minus 3 to the second power will annihilate that. Now, let's look at another set of annihilators. It turns out that d squared minus 2 alpha d plus a squared plus b squared to the nth power will annihilate all of these. E to the ax cosine bx as well as e to the ax sine bx and x e to the ax cosine bx, also x e to the ax sine bx, and x squared e to the ax cosine bx, x squared e to the ax sine bx. And this keeps going. Now, although the nth power will annihilate all of these, well, for n big enough, what you need to realize is that when n is 1, you need to use 2. You need to do the power 2. What's in that bracket to the what's in this bracket to the second power will annihilate this. What's in that bracket to the third power will annihilate this. Since there's an x to the 0 here, there's always one more. The power that you need in the annihilator is always one more than the power of x. When the power of x was 2, you needed to use 3. Now, what if you were just given cosine of x? What will annihilate that? You need to realize that this is e to the 0x, which is 1, times the cosine of x, which is 1x. That is, that's a, and that's b in this formula. So you have d squared minus 2 times a times b plus a squared plus 1 squared. That's the annihilator. We have to talk about the power as well. Well, this term is 0 and that term is 0. You just get d squared plus 1 squared. And of course 1 squared is 1. Now, what power do we use? Well, you need to also understand that I can always multiply by 1, and x to the 0 is 1. So, to be crystal clear, cosine x is equal to x to the 0, which is 1, times e to the 0x, which is also 1, times cosine of 1x. You add 1 to that power, you learn what power goes up here. That's alpha, and that's beta in this formula in the very top. Okay, so if you do d squared plus 1 on cosine x, you will get 0. You will get 0, that is an S. You will get 0, which is pretty cool. And to convince you, if you have cosine x, the first derivative is negative sine x, the derivative of that is negative cosine x. So the second derivative on cosine x is negative cosine x, and then you add 1 times cosine x, which is cosine x, and look, you do get 0. You really do get 0. So there's another host of functions that we know how to annihilate. And convince yourself that this works. You know, pick more interesting values for alpha and beta. You have e to the 2x, or x cubed e to the 2x cosine of 4x. Remember, that power is always 1 less than n. So n minus 1 is 3, so n is 4. And alpha is 2. That's A. And beta is 4. So the annihilator is going to be d squared minus 2 times 2 is 4 times d is 4d plus a squared plus b squared. Of course, I can just call that 20 to the third power. That's what it's going to take to annihilate this function. If we did d squared minus 4d plus 20, then not just 1 time. You have to do it 3 times. Well, like I said, n was 4, excuse me. You have to do it 4 times. And like magic, we end up with 0. Just do it 4 times and we end up with 0. Just pretty neat. The formula is very powerful. Okay, this differential operator annihilates all of these. And the lowest power that n can be is 1 more than the power of x, or the understood power of x. So that's pretty beautiful and everything. A little bit more theory, and then we can go into problems. So suppose, and this is very important, suppose L1 annihilates Y1. That is, L of Y1 is 0. And L1 is some differential operator. Maybe it's d squared plus 3. And also, suppose L2 annihilates Y2. That is, L of Y2 is 0. So now, what would annihilate that? Now what might this be? It might be 3x plus 4 plus e to the 2x. What would annihilate that? That's the question. Okay. Now, remember before I said d squared plus 5d plus 6? We can think of it as d plus 3 times d plus 2. And I did say, of course, didn't prove any of this. I did say that it can be thought of as that. And it really had nothing to do with us factoring. That is, yeah, d plus 31 times d plus 21. You could permute them. That's major. So what's going to annihilate this? The answer is it's going to be the product. The reason is because this is L1, L2 on Y1 plus L1, L2 on Y2. After all, L1, L2 is just one linear operator. Just like F circle G. It's one function. What on earth am I talking about? Well, remember, if you have f of x is x plus 3 and g of x is x squared, well then g circle f of x, this means g of f of x. And I know what f of x is, x plus 3. And I know what g does to whatever in the bracket. G takes what's in the bracket and it squares it. So I get x plus 3 squared. But that's the function. That's the function. If I said initially h of x is x plus 3 squared, you would go, okay. You would go, okay. Now, when you have linear operators or linear differentiable operators, they're linear. That is, maybe with functions it doesn't work, but with linear ones, you can switch those two. You can switch them. That's why I don't always call them differential operators. They're linear operators. Okay, so now what happens is I can switch these two. And I want to, because I want the L1 first. Remember, I think I said times, but that really means composition. Composition. So this here means L2 of that. That is L2 of 0, because L1, let me put the 1 there, L1 of 0 is 0. Likewise, I didn't switch anything in the second one, in the second term. Why? Because L2 was operating on Y2 first, and that's 0. That's 0. So I have L1 of 0. And anytime you do a linear differential operator on 0, you're gonna get 0. So a product works. So if you know something that's gonna kill one function, so you ever summer functions, and you know that L1 is going to kill that function, and L2 is going to kill that function, and L3 is going to kill that function, well then just do L1, L2, L3 of those three functions. Those are not zeros, they're functions. So you will get 0 back. Because L1, I'm saying L1 annihilates this function. L2 annihilates that function. That's given. L3 annihilates that. So the composition of all three will annihilate this whole thing. And that's important. Trust me on that. So that is why when you have 3x squared plus 4x plus e to the x. Now let's even get rid of the 4x. What's going to annihilate this? That's the question. Well, I know that these three will annihilate that. You take the derivative of the second degree polynomial 3 times, you're going to get 0. And e to the x is e to the 1x. So I know that d minus 1 will annihilate that, annihilate e to the x. Therefore, the product of these two, these 3 times d minus 1, it will annihilate it. Now, nobody's saying that you have to commute them. That is, nobody says you have to do the following. Well, this is these 3 d minus 1 on 3x squared plus these 3 times d minus 1 on e to the x. And then say, well, I want this to operate first. That is, I'll switch the two. D minus 1 times d3, 3x squared. You don't have to do this, because if you did, then it wouldn't work. You don't have to do it. Let's see if it works. Maybe I'm making this stuff up. So we do these 3 operated on d minus 1 of this function. So we'll do the third derivative at the end. We're taking the derivative at the end. First I take the derivative of what's in the bracket. I get 6x plus e to the x. Minus what's in the brackets. Minus 3x squared minus e to the x. Coincidentally, that cancels out. So now I have my quadratic. And of course d3 is going to do that. Because the first derivative will be 6x, it will be 6 minus 6x. The second derivative will be minus 6. The third derivative will be not 6, but 0. So it absolutely is working. And I didn't have to switch the order. And that's pretty nice that this stuff works. It's always nice when something works, isn't it? Now, to start getting ready to solving differential equations, I want to point something out. If you say have y double prime plus 8y prime plus 7y, this is the same as the second derivative plus 8 times the derivative plus 7 operated on y. Because after all, if you take the second derivative of y, you get y double prime. And then if you add on 8 times the derivative of y, you get 8 times the derivative of y, 8y prime. And then if you add on 7 times y, you'll get 7y. And this here is exactly what I started with. If you have 3y triple prime minus 7y prime plus 4. This is 3d cubed minus 7d plus 4. Basically, wherever you see y, you put d. And if there's dashes up there, you put the number of dashes. And you don't have to put the 1, okay? If you operate this on y, you get this back. 3 times the third derivative of y. Oh, that's that. Minus 7 times the derivative of y. Look at that, it's that. Plus 4 times y. Okay, this should say 4y, excuse me. That should say 4y. So you couldn't possibly have a constant on the left side. That is, you couldn't have plus 7 or plus 71. You couldn't. On the right side, you can have a constant. Because here, 3d on y, 3d squared on y, how about 3d cubed on y, gives you this, minus 7 times the derivative of y gives you this. But how do you get 71? So this wouldn't work. This just wouldn't work. So now we are in a position to try to solve a problem. I laid the groundwork. Hopefully I did a good job. And now we'll try to solve our first differential equation using the annihilator process. We have y double prime plus 8y prime plus 7y is equal to 3x squared. You need to understand the steps, but you also need to be able to state them, to memorize them. But you have to understand it. The first thing you do is you solve for the corresponding homogeneous equation. That is y double prime plus 8y prime plus 7y is equal to 0. And this is from an earlier section. The coefficients are all constants and homogeneous. The auxiliary equation would be this. When two numbers are multiplied out to 7 and add up to 8 isn't hard. Positive 7 and positive 1 do a good job. So m is negative 7 or m is negative 1. So the homogeneous solution will be c1e to the m1x plus c2e to the m2x e to the negative x. That is the homogeneous solution. Now so I'm going to leave that up on top so we have it for later on. Because remember, the general solution is equal to the homogeneous plus a particular. So I need to keep the homogeneous solution, because the question, maybe I should have stated the question. The question is find the general solution there. Okay, now we want to find a particular solution. And that's going to involve using an annihilator. If you want to annihilate 3x squared, we want to annihilate the right side, the g of x. If you want to annihilate 3x squared, you use d3. So I'm going to take d3 of the left side, and I'm going to do the operator d cubed on the right side. Now the left side, that was d cubed. Now I can write this as a linear differential. It's d squared plus 8d plus 7 operating on y. The right side is 0 because the third derivative of 3x squared is 0. Okay. Now we write the corresponding auxiliary equation. Instead of d, you write m. You have m cubed times m squared plus 8m plus 7 equals 0. M cubed you can't factor, so we can factor the other bracket. M plus 7, m plus 1. And so either that's 0, which is when m is 3, and its multiplicity of 3. The power is 3. Here, m is -7, multiplicity of 1, because the understood power is 1. We don't worry when it's 1. And here, we have -1. So, let's deal with the m equals 0. And just remember, so I'm going to start off with y1 equals c1 e to the 0x. But that's just c1. So y is c1, and then it's going to be x times c1 e to the x, e to the 0x. But that's always 0. This is just going to be x times c1 or c1x. Or c2x, excuse me. And then you're going to have c3x squared. Every time the multiplicity is more than 1, whatever answer you get, multiply it by x. Change the constant. Multiply it by x again. X becomes x squared. Plus c4e to the -7x plus c5e to the -1x. But these I already have. Those are the homogeneous solutions, or the solution to the homogeneous equation. So this here is my y particular. And we are going to use the same technique as before by equating coefficients to solve for C1, C2, and C3. We now know that a particular solution is in this form. It is in that form. And I'm going to plug that into this equation. But if I have the y, I need 8y prime actually, and y double prime. So let me calculate the primes. It's going to be c2 plus 2c3x. And the second derivative is just going to be 2c3. So I'm going to put everything I need below here. I just needed y double prime, so I already have it. Now I need 8y prime. It says 8y prime. So I'll multiply this by 8. I get 8c2 plus 16c3. And then I need 7y. So I'll multiply that by 7. I get 7c1 plus 7c2 x plus 7c3 x squared. Just multiplied by x. Just like you told me to. And I add. When I add all of this, I get 3x squared. Why? Because y double prime plus 8y prime plus 7y, which is right there, it equals 3x squared. When I add the right hand side, for the constant I get 2c3. Okay, now something has to be wrong here. 8 times y prime. This should just be an x here. 8 times that will be 16c3y. So the constant is 2c3 plus 8c2 plus 7c1. And the x's are just that sum. 16c3 plus 7c2 x, and 7c3 x squared this term. Now, you need to realize this left side is nothing more than the following. It's 0 plus 0x plus 3x squared. This must be 0. This must be 0. This must be 3. That must be 3. Okay, so what do we get at that point? We can solve for C3 right now. We can solve for C3. We know that 7C3 is 3. So C3 is 3 over 7. Alright? We know that that's 0. 16C3 plus 7C2 is 0. Bring that over, you get 7C2 is negative 16 times C3, which is negative 48 over 7. And if you bring this 7 into the bottom, you have 7 times 7 in the bottom, which is 49. So negative 48 over 49. Okay, now this last one, 2C3 plus 8C2 plus 7C1 is 0. But 2C3s, 2 of these, will be 6 over 7. 8C2s would be 320 and 64. 384 over 49. So it's going to be negative. Plus 7C3s equals 0. Get some more space down and we'll be in business. Equals 0. Now if I multiply top and bottom by 7, this bottom and this bottom will both be 49. So you have 42 minus 384 over 49 plus 7C3 is 0. 42 minus 384, I guess, is negative 342 over 49 plus 7C3 is 0. So this must be positive 342 over 49. Additive inverses. If you add, and we are adding, you're adding two numbers and you're getting 0. The numbers have different signs. That's negative 342 over 49. That must be positive 342 over 49. 7C3 is 342 over 49. Bring this 7 into the bottom. And know that product is 343. So I get what C3 is. I have C3, put all the values here. This value is C2, and C1, I guess I erased it. It's going to be 3 over 7. So let us write this up now. We're in a good position to write down the differential equation. general solution. It's C1, I'm copying this, it's C1 plus C2, which is negative 48 over 49x, plus C3 C3 x squared. C3 x squared. Now that's the particular solution. But the general is the particular plus the homogeneous, which I left up here. Plus C1 e to the negative 7x plus C2 e to the negative 2x. There is the general solution to that very top differential equation. This one right here. Like always, let's do some more. Suppose you wanted to solve y double prime minus 4y prime is equal to 2e to the 2x plus 3 cosine x. First thing is to find the homogeneous solution. Set it equal to 0. M squared minus 4m is 0. Factor out m. So either that factor is 0 or that factor is 0. This factor is 0 when m is 4. And of course, what should m be to get 0? 0. If m was 9, then m is 9. If I want to get 0, I'll let m equal 0. So, the homogeneous solution is C1 e to the 0x plus C2 e to the 4x. And since 0 times x is 0, and e to the 0 is 1, C1 times 1 is just C1. That there is the homogeneous solution. C1 plus C2 times e to the 4x. Now we want to find the particular solution. So we want to use an annihilator. What will annihilate 2e to the 2x? And the answer is d minus that number. And of course the brackets are completely backwards, but that's just notation. It's the theory that matters. D minus that number is what's going to annihilate a multiple of e to the 2x. Now, what is going to annihilate cosine x? Remember that cosine x is e to the 0x, which is 1, times x to the 0, which is another 1, times cosine of x, 1x. Well, that's a, that's b, and that's n minus 1. But it's from that big formula. D squared minus 2ab plus a squared plus b squared to the nth power. Well, if a is 0, then 2ab is 0, and a squared is 0. So you just get d squared plus b squared. But b is 1, and 1 squared is 1. And if n minus 1 is 0, if n minus 1 is 0, well, you all know 1 minus 1 is 0, so n is 1. That is, d squared plus 1 will annihilate, d squared plus 1 will annihilate any multiple, integer multiple, constant multiple of cosine x. So what's going to annihilate the whole thing? The answer is the composition. Which you write first is completely up to you. So I'm going to do d squared plus 1 composed with d minus 2 of this. But another way of writing that is second derivative minus 4 times the first derivative of y. And I'm going to do the same operation on the right side. D squared plus 1 composed with d minus 2 of 2e to the 2x plus 3 cosine x. And that right side is going to be 0. Is going to be 0 by design. By design, it's going to be 0. Okay. So you come up with the auxiliary equation. N squared plus 1 times n minus 2 times n squared minus 4m equals 0. And you try to factor, like I can factor an m out from there. I'll put that m way in front. So then I have n squared plus 1, n minus 2 times n minus 4 equals 0. So either m is 0 or m squared plus 1 is 0, which is when m is 0 plus or minus 1i, or when this is 0, which is 2, or this is 0, which is 4. And then we go back a couple of sections and we remember how to write down the answer. It's going to be c1 e to the 0x. But c1 times e to the 0x is c1 plus. It's going to be e to the 0x, which is 1, times c1 cosine of 1x plus c2 sine of 1x plus, okay, so this should be c2 and c3 plus c4 e to the 2x plus c5 e to the 4x. Then I look at my homogeneous solution. I have c1x, so I don't need it in the particular solution. And I have a multiple of e to the 4x, so I don't need this. That there is my particular solution. My job is to find c2, c3, and c4. So let me erase this. Let me put it on top, and then we write this down. We will find out what y double prime is, we find out what 4y prime is, and we subtract it. And we set it equal to this. And we equate coefficients. c2 cosine of x plus c3 sine x plus c4 e to the 2x. And we build up y double prime minus 4y prime. So I calculate the first derivative, get negative 2 sine x plus c3 cosine x plus 2c4 e to the 2x. Then I calculate the second derivative, which is negative c2 cosine x minus c3 sine x plus 4 c4 e to the 2x. Okay, and everything below here, I'm going to build up this. Why did I put the line there? Because the first thing I need is y double prime, which is right there. Now I'm going to multiply y prime, which is right there, by negative 4. So I get 4c2 sine x minus 4c3 cosine x minus 8c4 e to the 2x. And I add. When I add the left sides, I get e to the 2x plus 3 cosine x. Now let's add the right side. Let's combine cosine x's first. I have negative c2 cosine x's, and I am taking away or adding negative 4c3's cosine x's. Now let's do sine x's. I have 4c2 and I'm taking away c3. That's sine x's. Now how many e to the 2x's do I have? Well, I'm taking away 8c4's of them and I'm adding back 4. I'm really just taking away 4c4 e to the 2x's. Now, this has to be mathematically mature enough to know that the left side has also 0 times sine x. So this number must be 3, like that number. This number must be 0, like that number. And 2e to the 2x's, that must be 2. So negative 4c to the 4 is 2. So c to the 4 is negative a half. Okay. Now we have negative c2 minus 4c3 is 3. And 4c2 minus c3 is 0. If I multiply this top equation by 4, I'll have negative 4c2 minus 16c3 is equal to 12. In the bottom equation, I won't change. And if I happen to add these, this cancels. So again, negative 17c3 is 12. So writing it here, c3 must be negative 12 over 17. c3 is negative 12 over 17. Negative 12 over 17. Okay. Space going. If you subtract two quantities and you get 0, the two quantities are equal. 4c2 is equal to c3, but that just happens to be c3. On the left side, it's very favorable to divide by 4 to get c2. But I don't want to divide a fraction by 4. An alternative is to multiply by a quarter. And 4 goes into 12 3 times. Negative 3 times 1 is negative 3 over 17. Minus some silly error, that's exactly what C2 is. So at this point, we can write down the particular solution. C2 is negative 3 over 17, negative 3 over 17. C3 is negative 12 over 17. And C4 is negative a half. Negative a half. Now, once you have the homogeneous solution and you have the particular solution, and we do have both, Here's the homogeneous. Here's the particular. I can write down the general. It equals to the particular solution quiz plus the homogeneous solution, which is right up there. C1 plus C2 e to the 4th. Minus some arithmetic error, there's the solution. Don't get caught up on arithmetic error. The concept that you must understand. Do another one. You have y double prime plus 2y prime plus 2y is a function of x. One business. First step is you solve the corresponding homogeneous system. So the auxiliary equation will be this. It's going to turn out that m is going to be negative b plus or minus b squared, which is 4, minus 4 times a times c, all over 2 times a, which is 2 times 1 or 2. Now what's under here is negative a. I take that back. What's underneath there is negative 4. So we're going to have negative 2 plus or minus the square root of negative 4, which is 2y over 2. This gives us negative 1 plus or minus. This gives us 1i. So that's the a and that's the b. So the y homogeneous is going to be e to the negative 1x, or just e to the negative x, times c1 cosine of bx, which is 1x or x, plus c2 sine of 1x. So y homogeneous is e to the negative x times c1 cosine x plus c2 times sine x. So we may get rid of this now, and we go on and we find a particular solution. That is, we annihilate things. To annihilate e to the ax, you do d minus a. But a is 6. So we're just going to do d minus 6. That constant in front won't matter. Because when you take the derivative of that constant, you're going to get k times the derivative of that function. And when you do a times this, you can also factor out the k. The k factors out. And it derivative. And it turns out that what's in here is just d minus a on e to the ax. But that's 0. K times 0 is 0. Constant, in this case 5, will factor out. So we're going to do d minus 6 and operate on both sides. When we operate it on this, that can be written as an operator. D squared plus 2d plus 2 operated on y. And when we do this to the right side, by design, that's why we picked d minus 6. When we do it to the right side, we're gonna get 0. Okay. Now, if you started to see something, so now we get n minus 6 times m squared plus 2n plus 2. But that's and we set it equal to 0. But that's exactly what we had earlier when we solved the homogeneous equation. After all, what's the auxiliary equation for y double prime plus 2y prime plus 2y equals 0? The answer is this. So the only new one that's coming up is this. N is 6. So y particular is just going to be c1 e to the 6x. Now, if I found the zeros from here, it would just give me this stuff. And I always erase the stuff that was in yp that was also in the homogeneous. Alright, so according to this equation here, we have to go up to the second derivative. And according to that, we have to go up to the second derivative. So the first derivative will be 6c1 e to the 6x, and the second derivative will be 36c1 e to the 6x. And we want, copying this, we want y double prime plus 2y prime, which will be 12c1 e to the 6x plus 2y, which will be 2c1 e to the 6x. So we keep adding c1 e to the 6x's. So unless we end up with 0, we're going to end up with a multiple of c1 e to the 6x's. 36 plus 12 is 48, plus 2 more is 50. But this was really y double prime plus 2y prime plus 2y. That is, this right-hand side, when you add that up, you're supposed to get 5 e to the 6x. Well, that number must be 5. 50c1 is 5. And you should know if you divide that by 10, you get 5. c1 is going to be 1/10. Okay, so we're ready to write down the general solution. This is going to be the particular solution where I know c1. It's e to the 6x over 10, or if you prefer, 1/10 times e to the 6x plus the homogeneous solution, plus e to the negative x times c1 cosine x plus c2 sine x. There is your general solution. Now that wasn't so bad, was it? Try another one. Suppose you have y double prime plus y is 4 cosine x minus sine x. Well, the homogeneous equation will be that, and that means that m squared plus 1 is 0, the m squared is negative 1, the m is plus or minus 1, plus or minus I. In particular, it's 0 plus or minus I, or 1I. So that's the A and that's the B for the solution. Y homogeneous is e to the ax times c1 cosine of bx, that is 1x or x, plus c2 sine of 1x or x. And e to the 0x is 1. 1 times that is just that. So y homogeneous is c1 cosine x plus c2 times the sine of x. Now we want to annihilate. We want to annihilate the right side, generally called g of x. What's going to annihilate that? The answer is going to be b squared plus 1. b squared plus 1 is going to annihilate because cosine x is either the 0x, which is 1, times cosine of 1x. That should be x, please. That 0 is a. Thinking of that 1 being b. And when you plug that into b squared minus 2ab plus a squared plus b squared, you're going to get b squared plus 1. So if a is 0, that's going to be 0 and that's going to be 0. And 1 squared is just 1. So you have b squared plus 1. Okay. Just have to make one more comment. This is times x to the 0, so that's n minus 1. That is, n is 1 more than that. N is 1. You don't have to do 1. So that's the operator that will annihilate the right-hand side. So we're going to do b squared plus 1 on the left side, and the right, and this can also be written as d squared plus 1 on y. And when I do d squared plus 1 on the right side of 4 cosine x minus sine x, it annihilates it. I get 0. The left side is really d squared plus 1 squared on y is 0. That is m squared plus 1 squared gives us 0. Okay, so that means that m squared plus 1 is 0, and we just did it. That means that m is 0 plus or minus 1i. But the multiplicity is 2. Multiplicity of 2. Why of 2? Because the power is 2. Power is 2. That just means whatever you get from the first root, double root, just multiply it by x. You get that 1. Not sure what just happened there, but you get that y is equal to c1 cosine 1x plus c2 sine x. And I rushed through that because I just did it up here. Rewind the tape to see how I got that. Plus, since it's multiplicity of 2, I multiply everything by x. I get c3x cosine x plus c4 x sine x. And then I say, oh, look. This stuff is already in the homogeneous. That is, I'm going to just use that for the particular, including that plus sign. That is, if that plus sign was minus, I would say negative c3x. But it wasn't. So this here is my particular solution. And I can find c3 and c4. Okay, once you have the particular solution up to knowing the coefficients, that's when you plug it into the original equation. Y is equal to c3x cosine x plus c4 x sine x. And we need the second derivative. We need y, which I just wrote down. We need the second derivative. So I find the first derivative. It's going to be c3 times the derivative of that. It's a product law. The derivative of x is 1, which I won't write, times the cosine, plus x times the derivative of cosine x, which is negative sine x, plus the derivative of this, c4 times the derivative of that. The derivative of x is 1 times sine x, plus x times the derivative of sine x, which is cosine x. That's the first derivative. Now, the second derivative. The derivative of this is negative sine x minus this. Well, the derivative of this, the derivative of negative x is negative 1 times the sine x. And then the minus x times the derivative of sine x. We alternate taking derivatives. Plus c4 times the derivative of that, which is sine x, plus the derivative of that product. Derivative of x is 1 times cosine x, plus x times the derivative of cosine x, which is negative sine x. Clean this up a little bit. You get c3 times negative 2 sine x minus x cosine x, plus c4. Something bothers me there. The derivative of sine x is not sine x, sorry. Okay, cosine x times cosine x plus cosine x is 2 cosine x minus x sine x. That's y double root. And y is c3, just copying from here, cosine x plus c4x sine x. And I noticed that I have sine x's, I have cosine x's, x sine x's, and x cosine x's. So I'll combine like terms. I want to add those two equations. When I do that, the left side, based on the top equation, tells me I'm supposed to get 4 cosine x minus sine x. Right side. Let me combine sine x's. I only see sine x right here. I have negative 2c3 sine x's. Cosine x's. I seem to only have that one there. I have 2c4 cosine x's. Okay, did cosine x. What about x sine x? How many x sine x's do I have? So I annihilated that. X sine x. Well, I have c4 of them there. Oh, and look, I'm taking away c4. In fact, that just cancels out to nothing. And now we go to the x cosine x's. I'm taking away I'm taking away c3 of them. And look, I'm adding c3 of them being x cosine x's. Well, that cancels out. That is, this is all I get. This is all I get. Which is nice, because the coefficient of the cosine x's, they must be equal. 2c4 must be 4, which means c4 is a half. And the understood negative 1 must go with the negative 2c3. Negative 1 is negative 2c3, so c3 is a half. It seems like that both are half. Well, that makes no sense actually. Oops. 2 times 2 is 4. Divide both sides by 2, and you get c4 is 2. Okay. So I now know that c4 is 2, and that c3 is 1 half. Oops. C3 is 1 half. And there is your particular solution. And that's when you say, boy, I'm done now. All I have to do is add. Y general is y particular, which is this, plus the homogeneous. C1 cosine x plus C2 sine x. And that gives you the complete solution to that problem.